Bismillahirrahmanirrahim. Assalamu alaikum. Dear students, welcome you all in lecture 9. Okay. Uh, Basically, this lecture is also related uh, with the selection of cutting points, or you can say bending bars. So, in this lecture, basically, we are uh, dealing with the calculation of bending of bars, or you can say cutting of or cutting points. This is this example is also taken from MC Cormic book. We did one example in the beginning of this in the beginning of this lecture series of relating with the cutting bar in lecture 9, and now we are in lecture 8. Sorry, but this is another example, and this is a little bit extension of that lecture. Okay, and that we are just only calculate the theoretical points. Now we are extending our lecture to some in depth of these cutting points. Okay, so basically the example is that we have a rectangular beam, okay, which has four number 8 bars, and the bars is shown in the cross section of the beam. The beam depth, overall depth is 30 inch, okay, and the effective depth is 27 inches. The eff- effective concrete cover, you can say, the center to center concrete cover is 3 inches. The overall depth is 18 inches, and you see that the 3 at the rate of 4 inch means 4 bars, and their clear spacing is 3 inches. Okay, this 3, 1 2 3, sorry, these 3 are the spacing, and 4 inch they are center to center. Okay, and these are 4 bars. So basically total overall space, you can say, clear cover is 12 inches. Clear, this side cover and this side cover is also 3 inches. Sorry, bottom side cover, yes, this 3 inches side cover, this 3 inches side cover, and bottom cover is 3 inches. Okay, this is the simply supported beam having a UDL of 2.8 kip per foot. Fy is given, Fc prime is given 32 feet span, and this the reactions are given. Okay, what is needed and what is the demand is for determine the cutoff point for two of the bar, considering both the actual movement diagram and the required development length. Now here it says determine the cutoff points for two of the bars. Okay, so if we cut up two bars, so what will be the cutoff points? Okay, determine that those points, but here it you can say it restrict you, and that restriction is that the development length. This means that the cutoff length should be equal to or greater than cutoff length. Okay, development length should be greater than or equal to sorry, cutoff length should be greater than or equal to development length. So you must care for development length here. Okay, the cutoff length should be not less than development, because whenever we are basically in lecture 8, we don't uh, relating ourselves with development length. Okay, so whenever we are calculating the cutoff length, you know so you have to check that cutoff length with the development length of that bar, because the cutoff length should be such that must be equal to or greater than the development length, because the development length is that length in which a bar can develop its full strength. Okay, so if a cutoff length is less than the development length, this means that the bar will not develop the full stress, and thus the full moment capacity cannot be utilized. So because whenever we are making calculation relating to determining the moment capacity, like in the moment capacity equation, like this equation. No, this is not equation. Like the equation which we are, the basic equation for the moment equation, like whenever we are determining mn, okay, by mn. So whenever we are writing by mn equation, here we are basically if we are take 0.9, so a is fy d minus a over 2. Here basically this fy we are using, we are not using fs. So Fy means that the bar strength must be equal to that strength which we are utilizing our design. There may be 60,000 psi, or maybe 40,000 psi, maybe 75,000 psi. So this means that you have to provide a bar a development length. Okay. So for that, how much will be the development length for Fy value? Okay. So once you determine that development length for this strength. So now your cutoff length should be greater than this development length, which you are calculating for that specific stress. If the cutoff length is less than that development length, so this means that this Fy will not be developed. It will, the stress value will be less than Fs. So it will be less than Fy. There may be Fs. Okay. So therefore, your cutoff length should be greater than or equal to LD. Okay. So in this example, basically this kind of restriction is imposed here, that you calculate that cutoff length, but you must take care for the development length. You have to check the cutoff length with the development length. Okay. So this is the equation. You have 4 bars. If you cut up these 2 bars, okay, if you cut up these 2 bars, now what will be the moment capacity at that point, and at what distance we will cut those bars? Okay, so if I draw a cross section of that beam, let's say this is the beam. Okay, now at the mid portion you have 4 bar. Okay, at mid, but at mid you have how much bar? 4 bar. Okay, these bar are in plane. Okay, I just showing you in cross section, and at cutoff point you have to continue only 2 bar. Okay, you have to continue only 2 bar. Now the question is that you should need to calculate this distance, that how much this distance is from the support. What will be the value of that distance? Clear? That L1 distance will be how much, or you can say that cutoff length will be how much. Okay, now first of all you have to check. Okay, because the phi value, okay, you have to check the phi value, that whether it is equal to 0.9 or not. Okay, so for that purpose you need to determine the rho value. Okay, the ast is given, that is 4 number add bar, so divide a is divided by the width and dd. Okay, the width and the depth of the beam, it will give you rho. Okay, uh, and then you have to determine rho max value. Okay, that can be taken from the table, as in example 1 we did in lecture 9, in lecture 8, sorry. So from there, and you have to determine rho minimum value. Okay, so basically all these calculation is same like we did in the design of rectangular beam. Okay, so there you can use the formula fy, or it must be greater than or equal to 3 under root fc prime divided by fy. So select them the maximum value from these two. Okay, that will be your rho minimum. So if the condition rho provided is greater than rho minimum but less than rho max is satisfied, this is the ductility check. If this ductility check is satisfied, then your p value will be 0.9. Okay, so once you have do this check for 4 number bars, 4 number add bars, and after that you have to check this. You have to check. You need to use this check also for 2 bars, and you need to check that whether when you are using your 2 number of bars, whether the AST is more than row minimum or not. Okay, so 4 number 8 bar give you an AST of I think so 3.14 square inches. Okay, that is given here. 4 number 8 bar give you this much AST. Now if you cut off 2 bars, okay, if you cut off 2 bars, so obviously this area will become half because you discontinue 2 bars, so this will become half. Then you need to provide row provided, you calculate it, row provided, and then your row minimum value will be the same, row maximum value will be the same, and then you need to check this. Okay, row provided should be greater than row minimum, because in any case this will be row maximum. In all cases, you this is the basic criteria, this is the basic criteria of ASCII code, that your row provided should be greater than row minimum. So basically he did this check here, that and you also need that whenever you are using your AST, okay, first of all you need to did this check, and then you need to determine the moment capacity. If this check is okay, if this check is okay, then you proceed further, and if this check is not okay, then you can't cut off 2 bars, then you need to continue 3 bars. Okay, you can cut 1 bar. Okay, or after that the check is not accomplished, then you can't, then you cannot basically cut off the bars. Okay, in all cases this check should be satisfied. Okay, so basically if this check is satisfied, then you need to proceed further, and you need to determine now the moment capacity of the 2 bars. Okay, from you will select this steel area. Okay, you will select this area, and you will use the basic moment equation right now, this equation. Clear? Where I write it, I remove it, but the basic equation, that is A is Fy and D minus A over 2, and you will calculate A. How you can calculate it? A is equal to A is Fy divided by 0.8 Fc prime into B. Clear? So S will be what? S will be the half of the this 3.14, half value. Okay, because you are providing 2 basic bars. So basically here they did this step. Okay, they say the design moment capacity of this beam has been computed to equal to 359.7 foot kif when it has 4 number add bars. Okay, when it has 4 number add bars, the design moment capacity for 4 number add bar will be this one, 359 point. Basically this means that when you draw the moment diagram, okay, when you draw the moment diagram, the peak value will be 359.7. Okay, now this moment capacity is for 4 number add bar. Now they are basically determined that when we discontinue these 2 bars, so what will be then the moment capacity at this point? Here we can discontinue 2 bars. We cut up 2 bars and we just only continue 2 bar. Here the bars are 4. Okay, but here the bars are now 2. So when there are 2 bars, how much will be the moment capacity? And he calculated it that it will be from this equation. Okay, he calculated that moment capacity from this equation. Phi mn 0.9 is put the value of half of that 4 number add bar, you need to calculate two number at bar. So this s will be 3.14 divided by 2. Here put that value, put the fy value, d minus a will be from there. Their s value will be equal to this value. Okay, it will give you the a value. Putting that value, you will get the phi mn value, and that value will be 185.34 K. Okay, that value will be for now two number at bars. Okay, this value will be 185.3. So if you check it, this value, if you if you if you consider the half value of this value, it may be around about, it will be, you can say this will be the 30% of this value. Okay, no, sorry, 50%. So you have 359. Okay, you have 359. Yes, 359.7 divided by 2. So 179, say 180. So you can say this is around about 50% of the maximum value. Okay, that will be the round about 50% of the this 359 value. Clear? This will be give you round about 185. Okay, so now basically at the beginning of this lecture series in lecture 8, I I already define you that if you are providing 4 number add bar for this kind of movement, so if your movement capacity, now if your movement becomes 50% less, so there will be obviously 50% less bar will be needed at that point. Okay, this is the basic, you can say basic mechanism of cut up bars. So basically he check it that if you are providing two number add bar, now he basically calculate row provided, two bars. So two number add bars give you 1.57. Okay, that will comes out from 3.14 divided by 2. 3.14 dividing by 2 give you 1.57. Clear? And divide that ast by the width and the depth of the beam section give you, okay, this is the value of row provided. Clear? And now row provided is, your row minimum value will be 0.0033, and your row provided value will be 0. Your row provided value, that is 0.0032, and your row minimum value is, that is 0.0033. Now the row minimum is less than row provided, but here they make that assumption that the both the values are very close to each other, so therefore they just assume that, let's say, row provided is approximately equals to row minimum, because they are at, both are, you can say, at the verge. Okay, so row provided will be 0. That is basically calculated from fy divided by, sorry, 200 divided by fy from this formula. Okay, this is the controlling formula. Clear? Now here basically, but is considered to be close enough. Okay, in addition, now he calculated ld. Okay, now the basic, the whole procedure which I will did in, I think so, in lecture from lecture 2 to lecture 5, lecture 6, basically those lectures on the basis of the calculation of ld, that how we calculate ld. Okay, so you have to, and this example is solved. Okay, this example is solved in the same MC Cormic book. So if you recap your lecture 4, lecture 5, I will did this example, okay. So but in that case, the bars are top reinforcement. That is, the reinforcement is top reinforcement. So the same question is solved in the book, that is example number 7.4, okay. You can read that example 7.4 where the bar are at the top. So your psi uh, t factor, okay, there is 1.3. So here basically you have to consider psi t factor is 1, and in the calculation for the development length in this example you have to consider this psi t equals to 1, not 1.3. And basically he did this example in 7.4. Example 7.4 is just like this example, okay. So you knew I don't want to waste my time on that calculation, okay. The side covers are given, okay. This is the bottom cover, okay, and this is the side cover, that is also 3 inches, okay. This is also 3 inches. So side cover, bottom cover, both are 3 inches. You have to, and remember that this is center to center distance, okay. So you need to calculate the center to center distance of these two bars, okay. This 4 is given. Basically the clear distance between these bars is given, that is 4 inches. Clear? So you just need to calculate the center to center distance. That center to center distance will be 4 plus half of this bar and half of this bar. So number 8 die is 1. So you just divide 1 by 2 plus 1 by 2, okay. It will give you 5 inches. And for if you are, when in this example when you are calculating your development length and you are calculating your psi b cb factor, okay, cb, what will be the controlling cover, okay. So then you have to take the half of this center to center spacing, and that will be 2.5. So your your bottom cover is 3 inches, your side cover is 3 inches, and your half of the centers will be 2.5. Now this is the controlling controlling cover. Your CB will be now this value. So in the basic formula which is written for, which is given for the calculation of LD, okay. And that formula, we are using exposing factor, we are using psi t factor, and we are using um, sorry, that is the quoted factor, that you must consider at 1, okay. You must consider it 1. Psi t will be 1, and uh, psi, what will be that factor? The next third factor is uh, size factor, psi s. So the bar is the more than 6, so this factor will also be equal to 1. Clear? And the rest of the thing you should need to use, okay. You should need to calculate KTR, ATR, and the spacing is given in this 7.4 example, okay. The stirrup spacing is given, that is this is equal to 8 inch, and number 3 which is given, okay. So number 3 stirrups at the rate of 8 inches to so your ATR will be this one, 0.22. Clear? And your spacing, number of bars in value in the calculation of CB KTR, you need to use, so in 1 2 3 4 you need to use 4, okay. So you just need to recap that example number 7.4. You will get that how we can calculate LD. So from there your KT value will be this one. From there lambda value, you will consider lambda value will be 0.75, okay. So he did not say anything about that, whether it is um, lightweight concrete or whether it is normal weight concrete, okay. So you consider lambda is equal to 0.75 and you check it that whether LD comes out to be 41, okay. If not, then 41 inches. If it is not comes out, then you need to put lambda is equal to 1, okay. So first check it with this value and then check it for one value. So when you do all of your calculation, you get this value. Clear? So up to this point, I think it is clear. Okay, this is the same calculation which we previously did in development length calculation, and the first initial step is basically you need to recall your design of your reinforcement. Okay, so you need to recall your that design story of rectangular beam. Okay, so after this, the calculation is now become a little bit tricky. Okay, so now, okay, we are basically concerning with cut up bars. Okay, cut up points. Okay, that where those points lies. Okay, so this is the beam. Clear? And these are the support reaction. Okay, you see that there, in between these 2 points, there are 4 bars, but behind these 2 points, there are 2 bars. Okay, which is continue to the supports. Clear? Now the question is that, that what will be the design capacity of this bar, of this beam. Okay, if the loading is given, okay, loading is already given. Okay, so first of all, you need to calculate your moment capacity. That what will be the moment capacity. Clear? What will be the maximum moment capacity? This is 2.8. So you need to solve this question for bending moment diagram. If I did this in SAFE, so mm, let's say I do it. If I do it in the SAFE, you will see that is 32 feet. Span is 32 feet. Okay, this is the beam. This is, so let's see, check if joints are okay. This is hinge and this is ruler. Okay, now we assigning the load, distribute it. We just make it 0. That don't consider the self weight of the beam. Okay, and we just putting in the value 2.8 kip per foot. Okay, 2.8 kip per foot. Okay, now analyzing. That will be design. Let's see. Now, this is your design moment. Clear? This is the maximum moment that comes out from the formula W is square by A. So now this is the maximum value. Clear? Which lies at a distance of a mat span. Clear? Now, if this is the design moment capacity, then what you need to draw? You need to draw basically the moment capacity envelope. Okay, the moment capacity envelope is a kind of, you can say, it is a kind of uh, mm, movement diagram. Okay, it is a kind of movement diagram. like basically, लेकिन उसको हम कैलकुलेट करते हैं किस बेस पे? उसको हम कैलकुलेट करते हैं on the basis of rebar, on the basis of not on the W square by 8 formula, and not on the basis of the mathematical equation, which is basically based on a on the which is basically based on shit, which is basically we draw basically you must see that whenever we are calculating the design moment capacity, sorry, the cutup points, we need to draw two types of moment diagrams. One moment diagram is basically drawn for the actual movements, okay, which comes out to be like somewhat like this. Clear? And we see that maximum movement lies at the midspan, and that is around about 359. Clear? Around about 359. Keep put. Then you need to draw the movement diagram, which is drawn on the basis of what formula? Which is drawn on the basis of min formula. Clear? Which is drawn on the basis of P Fy As into D minus A over 2. Okay. Now you need to draw this movement diagram on the basis of this formula. Okay. Now basically at the support, as we see that the moment is 0, but at the mid span the moment is maximum. So here is it is also the same criteria works here. Okay. Now uh if I check, if I draw both these lines, okay, if I just show you this moment diagram here, okay, you know this is a kind of, I draw the points of this diagram here. Okay. Now my this moment diagram, basically the diagram which I construct on the basis of this formula, it should be, its moment capacity should be greater than these values. Okay. Because we design, almost whenever we are design, we say that phi mn should be greater than mu. This is the basic criteria. Okay. 350, this is the mu. Clear? This is the mu. Clear? So if I provide, as I already told you, if I provide 2 bar, clear, if I am providing 2 bars, what will be my phi mn value? And I did that calculation and I got the value that is 185. Clear? That is 185. Now if I am drawing the moment capacity, or you can say capacity moment diagram. Okay. So let's start, we assume that diagram, you know and you must know that this 185 lies at this point. Clear? At this point. Clear? So I will I basically I directly join the support point with this moment moment capacity. Okay. 185, this 185. And remember this line basically showing you the moment capacity. Okay. Now it should be remember, that why the moment capacity at this point is 0. Why? What is the reason? Because at this point also there are 2 bars, and the same A is the same D, the same A, the same thing is also exist here. But the moment capacity is considered to be 0 at this point. Why? The reason is that now at this point the bar not sufficient length to develop this stress value, because the bar is on the point. Okay. if I explain in basically more explain, इसके कहने का मेरा मतलब ये है कि यार इस पॉइंट के ऊपर भी तो यही एस है, इन 2 bars इधर भी है. ओके. 2 bars are also present at this point. ओके. ये बीम की जो डेप्थ है वो भी सेम है, सब कुछ सेम है, लेकिन मोमेंट कैपेसिटी यहाँ पे क्यों इस तरह नहीं है? क्यों नहीं है यार? क्यों इतने लेंथ कवर करने के बाद हम 185 लेते हैं? द रीजन इज दैट that the bar here, यहाँ पे जो है बेसिकली Fy है, Fy, और ये Fy यानी ये स्ट्रेस जो होती है बेसिकली, this stress is basically developed when the bar is embedded into the concrete. The bar is embedded into the concrete up to a length which is equals to LD. If a bar is not embedded, for a development length, it will not give you the stress that is equals to Fy. Okay, so therefore I select this point. I select this point. Clear? Now at this point my stress must be equal to Fy. If not, then my stress will not, then the moment capacity will not be equal to 185. It should be clear, and that is the point which we which we are uh, uh, that is the point which we are basically we basically justified, we basically check in the calculation of whenever we are calculating the cutoff points, that जब भी आप cutoff point select करते हैं, so your cutoff point should be lies at a distance at which the stress value must be equal to that value at which you are did that calculation. Okay, यानी कि आपने इस इक्वेशन में Fy की जो वैल्यू डाली है, आपने आपने बार को इंश्योर पर करना है कि आपकी जो स्टील बार है उसमें वो स्ट्रेस जो है वो बेसिकली डेवलप हो। इस पॉइंट के ऊपर ऑल दो dimensions are same, steel area is same, but the bar embedment is not sufficient to give you that value of stress. So whenever it must be, because the basic purpose of calculating the development length is that how much I will embed my bar into the concrete, that will give me my design stress value Fy, and that development length which I will calculate it, that is 41 inches. So basically I select this point, this cutoff point. Now I will check that cutoff point. Okay, so this is basically now the cutoff plane at this point. And the one thing you must ensure that at cutoff point, the actual bending values should be less than. Now this is this is your you can say this is the design capacity envelope. Okay, now after that we basically we see that these points are below from this. You just draw a straight line, will cut it at this point. Now you know that if I consider it, you must need, because it will go up and then it will go down. Okay, so this at this point the value will be 359. Clear? The value will be 359. Clear? Now you need to what you need to increase now your value to to reach this value. Clear? So therefore basically here uh, we calculate this distance also, because after this point you need to provide 4 bars. Clear? You need to provide 4 bars, and that 4 bars give you a moment capacity of 350 it will give you 359.7. okay, it will give you this value is 358. okay, this is 358. And when you are providing number 4 bars and you calculate the moment capacity from this formula, when you are using 4 number at bar, it will give you at this point basically how much? 359. So 359 is more than 358. Clear? So it will come and then it will come down and at an inclined line. Then it will go same and then it will come down. Okay, so clear, this is again 185. Clear. So this is the capacity envelope. Okay, and this diagram is basically, you see here that this is the actual movement diagram. Okay, this is the actual movement diagram, this one, which is based on WL square by 8 and something like that. But the the shaded line which you are seeing here, this is the capacity envelope. Okay, this is the movement diagram, which is the based on the strength of the beam, and it is purely based on the steel and depth of the beam. Okay, so now from this point, this is basically this is the first theoretical point. Clear. this is the this is the theoretical point. Clear. This is the theoretical point. Clear. After that, it remain constant, and up to this distance. Clear. And then from this distance, okay, from behind this distance, uh, and between these 2 points. Clear. This is 185. It remain constant. Now in between these two bars there are four number 8 bars. So due to these 4 bars, the moment capacity become increases, and it will comes here. Okay, it will reaches here, and then it remain constant and then coming down, because at this point we are providing 2 bars. Now the question is that this is the first theoretic, this distance is the first theoretical point. Clear. Now this distance must be equals to development length. Clear. This distance must be equal to development length. Clear. And you can see that this is equals to 3 foot 5 inches, which is 3 foot with 5 inches is 41 inches. Okay, this distance must be equal to development length. Clear. And this distance will be equals to 1 foot 5 inches. Clear. 1 foot 5 inches. So basically, you know this is the, you can say, this is the actual cutoff point. This is the actual cutoff point. This is the theoretical cutoff point. This is the actual cutoff point. And the actual cutoff point will be 3 foot 5 inch plus 1 foot. So 4 feet, 4 feet and 10 inches. Clear. At 4 feet and 10 inches is the actual cutoff point. Okay, so this is the basic length. Okay, now you see that at this point the moment capacity is equals to 359.74 kg. Okay, so now here you can see that there is 359 and here is 359. So this envelope is more than that is the ultimate moment capacity. So the beam is now safe. Clear. Now you see that now you need to calculate the length of 4 number 8 bars. That how much will be the continued length of 4 number 8 bar. This 22 feet and 4 inches. Clear. This is the length of cutoff bars. Behind that, behind this point, okay, there are 2 bars, 2 number 8 bars. Clear. So basically this kind of calculation you need to ensure. Okay, so if I read this paragraph, the solution for this problem is shown in figure this. There are 2 bars beginning at the left end of the beam. 2 bars, you see there are 2 bars which is beginning from at the left. Okay, you see it. Because no development length is available, the design moment capacity of the member is 0. I already mentioned you. Okay, why at this point the design moment capacity becomes 0? Because there is no development length available. So when these 2 bars covers a distance which is equals to development length, then it will give you strength. And I will show you that value, that that explanation, that why at this point 185. It is also at this point the design moment capacity should be 185, but not because there is no development length which is available for the bar. Okay, so due to that, the design moment capacity is not equal to 185. When it covers a distance equals to LD, then it gives you that 185 value. Okay, clear? If we move a distance LD from point A, okay, if we अगर हम point A से move करें up to how much distance? LD distance. Then it says at the left end of the beam to point B. Now हमने point A से point B की तरफ LD distance cover किया, ठीक है? The design moment capacity can be approximated as a straight line from 0 to 180. Now this line you can achieve. Okay, this line will be achieved. The design moment capacity can be approximated as 185. From point B to C, it will remain equal to 185 because you know that the design line, the ultimate moment capacity line you see, which is well below from point B. So if you draw this straight line, you will touch the ultimate moment bending moment diagram. Okay, so at point C you touch the actual moment. Clear? Now from there you can't go straight. You need to jump above. Okay, आपने basically इस dotted line से ऊपर जाना है. You need to go up from this dotted line. Clear? So now अगर आपने ऊपर तक जाना है, जिस तरह हमने बेसिकली यहाँ पे इस लाइन को खींचा, तो आपने you need to cover LD. okay? इस C से जब आप LD डिस्टेंस पर जाएंगे तो तब आपको ये 359 स्ट्रेंथ अवेलेबल होगा. अदरवाइज यू कांट. अगर C से इस D तक का डिस्टेंस आपका LD के बराबर ना हो, हॉरिजॉन्टल डिस्टेंस, तो याद रहे कि आपको 359 स्ट्रेंथ मुयसर आपको नहीं होगा. ठीक है ना? तो ये बात बेसिकली जरूरी है कि पॉइंट ए से पॉइंट बी तक का डिस्टेंस LD होना चाहिए, तब आपको 185 मिलेगा. इसी तरह पॉइंट सी से पॉइंट डी तक जो है आपको LD के बराबर डिस्टेंस, हॉरिजॉन्टल डिस्टेंस कवर करना है, तब आपका जो स्ट्रेंथ होगा 359 होगा. अदरवाइज the strength will not be equal to 359. Clear? After this point D, you remain constant, okay, and then you are going down. The same thing like that. Now, अब यहाँ पे क्वेश्चन ये है कि आपको इस पॉइंट के ऊपर बेसिकली 358 होनी चाहिए, लेकिन 358 बेसिकली यहाँ पे जो स्ट्रेंथ है वो 359 है. So you are on the safe side. 359. Clear? Now the basic theme of this whole question is that your bar must be embedded at this center point of the beam on both sides, this side also and this side also. Okay, if you want that your moment capacity of your beam will be 359, your bar must be embedded into the concrete both sides from this point equals to LD. अगर आपका बार इस पॉइंट के दोनों साइड पे LD के बराबर एम्बेडेड ना हो, so you should be remember कि the design moment capacity of your beam will not be equal to 359. Clear? अगर आप 359 moment capacity चाहते हैं, so your length must be embedded from of this center point to both sides must be equal to LD. दोनों साइड पे ये एलडी होनी चाहिए। इसी तरह अगर आप इस पॉइंट पे 359 चाहते हो कि the design moment capacity of your beam must be equal to 359, so if you draw this point on the beam, so इस पॉइंट के दोनों साइड पे, इस पॉइंट के दोनों साइड पे आपका जो बार है बेसिकली it must be embedded into the concrete up to LD distance, both साइड पे, दोनों साइड पे बार एम्बेडेड होनी चाहिए LD पे, ओके, दोनों साइड पे, तो तब जाके आपको बार 359.7 स्ट्रेंथ देगा। इसी तरह अब इस पॉइंट पे आते हैं, सो इस पॉइंट, अगर इस पॉइंट को मैं बीम के ऊपर ड्रा करूं, तो इफ यू वांट that your design moment capacity will be equals to 185.3, you must to ensure that your bar should be embedded into the concrete up to LD distance. If it is not embedded, means the bar is not inserted into the concrete up to LD distance, your design moment capacity will not be equal to 185. Remember. And similarly, up to this side also, both left and right of this point, your bar must be inserted, or you can say it must be embedded into the concrete for a length of 185.3. Okay, so then the design moment capacity will be 185. Is, you can say, the whole theme of this question is that clear कि किसी भी पॉइंट के ऊपर आप डिजाइन मोमेंट कैपेसिटी कैलकुलेट करते हैं, तो उस पॉइंट पे आपको वो डिजाइन मोमेंट कैपेसिटी तब मुयस्सर होगी जब वो बार उस पॉइंट के दोनों साइड पे डेवलपमेंट लेंथ के बराबर कंक्रीट के अंदर एम्बेडेड हो, तब आपको वो बार जो है वो आपको, अगर वो 2 बार है या 4 बार है, जितने भी है, वो आपको उतनी मोमेंट कैपेसिटी देगी। ठीक है, दूसरी बात which is very very important is that how this this length is achieved, how this length is achieved, this LD तो बेसिकली हमने कैलकुलेट किया, क्लियर। नाउ अब ये जो 22 फुट 4 इंचेस है, ये बेसिकली कहाँ से आया है? सो you should need to remember this question. This is MU, basically it is right section diagram that how this 74 comes out. Okay, it lies at a distance of 8.25. You can you see that at this point, D point, what will be the actual moment capacity, what will be the actual bending moment, that is 274.3. how it comes out. Okay, ये वैल्यू कहाँ से आई? तो इसके लिए आप, जाहिर सी बात है, आप सेक्शन इक्वेशन लिखेंगे। जिस तरह हम इक्वेशन लिखते हैं, आपके पास रिएक्शन यहाँ पे 44 है, क्लियर। आप डिस्टेंस x के ऊपर क्या ले, एक इक्वेशन लिख ले, और आपके पास UDL है, साथ ही साथ आपके पास रिएक्शंस है। सो यू कैन राइट द इक्वेशन फॉर MU, ओके, 44 मल्टीप्लाई बाय x माइनस 2.8 multiply by x into x divided by 2. Clear? So you just draw, you will just do this calculation, taking x is equal to this much. Okay, this much. No, yes, this much distance. Putting this x is equal to 8.25. So 3 foot 5 inch plus 1 foot 5 inch plus 3 foot 5 inch, it will give you 8.25 feet. So at this distance you will calculate the MU, which will be equals to 274.3. clear? Okay, so basically they did this calculation. The rest of thing is simple. Okay, the main theme is that, okay, at point C we reach to that value. Okay, now the question is that you need to determine the this distance, okay, from C, that how much distance is from C to A. This distance is how much. Okay, So you can calculate, because at point C you know the moment capacity, which is this one. So from the same equation which I wrote here, from same equation, this equation, because you know the moment capacity, okay, mu, if you write the moment equation, that is x minus 2.8, you know, so basically we write the moment equation, as we know that at this point C we having the capacity of the beam, which is 185. So if I write this equation, okay, the same equation which I write here, and I compare, because this phi mn at this point C is equal to 185, so I just put 185 44 and I did the calculation, which is a quadratic equation, and for x I get 4.88, which is equal to 4 feet 10 inches. Now this C point is basically, this is my actual point, cutoff point, okay. This point is basically lies at a distance of 4 feet 10 inches from this support. Clear? This distance is 4.8 inches, 8 feet, okay, which is 4 feet 10 inches. Now you know the development is 41 inches, okay, that is 3 feet 5 inch. So just subtract 3 feet 5 inch from this 4 feet 10 inches, you will get 1 feet 5 inch. This constant distance, the moment which remain constant, is 1 feet 5 inch. Clear? So I think this kind of calculation is not tricky, it is simple calculation, you know. And similarly, the they also did by the time we reach point D, 3 feet 5 inch from C to D. You know, this is also necessary. Okay, this means that if you are start from C to D, you must need to cover LD distance. So at a distance LD, you will get this value. Clear? I already mentioned you. So if I summarize my uh, whole lecture, the main theme of this lecture is that you need to basically draw what you need to basically draw the moment capacity diagram plus your actual moment capacity diagram, your actual moment diagram, which is based upon the actual loading. Okay, you can draw it in safe, you can draw it in manually as you read in engineering mechanics, and then you need to draw the moment capacity diagram, which is based upon what, which is based upon your aci and 0.9 and that the basic formula. Okay, so once you did draw your actual moment diagram, clear, and then your capacity diagram, clear, which somewhat like this as in the present case. Okay, clear. Now you need to take this diagram and just fit it into this diagram. But before doing this calculation, you need to draw first of all this diagram, and then you need to draw the capacity diagram. Clear? And then you will need to calculate those points, like this point, clear, like this point, clear, like this point, clear, and like this point. So as you know the moment capacity at this point, because at this point you have two bars and the two bars capacity is 185. Clear? So 185, okay, and as it remain constant, so this distance must be equals to LD. So the theme of this question is that at every point, you know, at every point, if you are entrusting that if you draw your capacity diagram, okay, if you draw your capacity diagram, which is this is the moment capacity diagram, you know, which is based upon the phi mn value. Clear? Phi mn, that is the basic PRC formula. Okay, so A is Fy, d minus A over 2, and you draw this moment diagram. If you are interested that if you get a value at this point, let's say this is 300, so your 300 value you will be achieved if your bar length embedded into the concrete for a distance of LD. कहने का मेरा मतलब यही है कि इस बीम में इस पॉइंट के ऊपर अगर आप चाहते हैं कि मेरी मूवमेंट कैपेसिटी 300 हो, तो इस पॉइंट के दोनों जानिब कंक्रीट के अंदर आपका बार LD डिस्टेंस तक एम्बेडेड होनी चाहिए. अगर ना हो तो then your movement capacity will not be equal to 300. So this is the main thing, okay, of this lecture. And after that lecture, inshallah, we will recall some theory in the in Nelson book. So he basically illustrate these things in more detail. Okay, this is after that we will did that calculation in more detail. Okay, so up to this point, I think it is enough, because in Nelson book this calculation is most tricky, most complicated, and there we will consider the effect of shear moment. What will be the effect of shear on this cut up points and cut up bars? Okay, so we consider those effects, and then we inshallah wind up with this topic. Okay, so if you have any question, any doubts, I welcome.